Welcome everyone back to another episode of DentChem. This is going to be an example video on identifying electron-rich and electron-poor sites. So you've watched the instructional video, we understand our electronegativity trend, and we also need to remember that alkenes are going to be electron-rich. Those two simple things for maybe the most important tool in all of organic chemistry. This is where who has electrons and who wants them, that's where all of that starts, right here. You try these examples on your own, and now we'll compare answers. First thing I see here on this example, I have two halogens. Those are really going to be electronegative. Okay, so they're going to be pulling electron density towards themselves, and the carbons bonded directly to them are going to be mostly affected. So they're going to get that partial positive charge. Now, fluorine is more electronegative than iodine, so I would expect this difference in here to be greater than the difference between these two. Bond overlap might have an effect on this, but that's too advanced and not really important for our sake. This is definitely enough at this level of organic chemistry. If we want to identify electron rich and electron poor over here, I notice that nitrogen, okay, is my most electronegative atom here. And so it's going to have a little partial negative right there. And it's going to affect the carbon it's bonded to. Simple as that. Down here, I have a acid halide, acid chloride group here with a carbonyl bond. Okay, I have an oxygen that's pretty electronegative, chlorine really electronegative, okay? And the fact that I have a double bond also is going to increase that difference. So I would expect oxygen to be pulling electron density towards itself because it's bonded to a carbon. And that carbon is also being affected by that chlorine there. So lots of pulling from both that carbonyl bond and the chlorine on that carbon. And as a result, we get a really large partial positive on that carbon, a really reactive site there. Not only chlorine a good leaving group, but the main thing we're worried about here, large partial positive on that carbon. Not only we have that carbonyl pulling on it, we have that chlorine pulling electron density towards themselves, greedy electronegative atoms, and it leaves a big partial positive right in the center. Hemiacetal group right here. Doesn't matter if we know that or not. We can still identify electron-rich and electron-poor sites. Oxygens are going to be the most electronegative here. So they're going to be pulling electron density towards themselves slightly. And most affected is probably going to be this carbon right down here because it has two oxygens pulling electron density away from it. These would be slightly affected up here, but not as much as this, only because it's the only carbon where two oxygens are pulling from it. So this is a good representation of where we would expect the most partial positive and most partial negative to be. And lastly, we have a thiol there. Sulfur is going to be slightly more electronegative than carbon. Actually quite a bit, maybe not as much as oxygen, but it will be more electronegative, partial negative, electron rich, partial positive, electron poor. And so if we introduce, let's say, a nucleophile here, nucleophiles, remember, have a lot of negative charge, okay, and opposite charges attract. So nucleophile who has electrons are going to attack electrophiles who wants electrons. Negative and positive attract. So if I have a negative nucleophile, we would expect it to attack positive areas, right? Positive or opposites attract. So our negative nucleophile is going to attack positively charged areas, okay? Our partial positives. So if I introduce a nucleophile here, I would expect it to attack this carbon right here, most likely. Attack this carbon right there. Attack this carbon down here. Attack that carbon right there. And right there as well. I'm not including iodine carbon bond just because I think the fluorine carbon bond would be more likely in that case, okay? this is going to be the bulk of all of our mechanism arrows. Who has electrons and who wants them? You'll be able to predict a lot of mechanisms with just this simple rule. This is going to help out a ton. I hope DentChem helps out a lot as well. Thank you for watching. Tell your friends about DentChem and make sure they subscribe as well, because you already have.